All right, moving on. Our next keynote is going to be delivered by Martin Roetteler. He's the Senior Director of Quantum Solutions at IonQ. The title of his talk is Toward Quantum Commercial Advantage with Enterprise-Grade Quantum Computers. Martin, are you here? All right, please, welcome.
Thank you for the introduction. My name is Martin Roetteler. I lead the applications team at IonQ. I think Dr. Vahedi put it very nicely in the morning. He said, he speaks from the heart. I want to do the same here and give you an overview of our work with existing customers in various different verticals, and also give you an idea of what the first-party application stack looks like at IonQ, where we place the bets into which applications seem very promising. Got to start with a disclaimer. As a public company, these are forward-looking statements or might contain forward-looking statements. And it's always a good idea to start with a mission statement. So we want to build the world's best quantum computers to solve the world's most complex problems. And as many of you know, we have a product fleet. The current generation of the system is called Forte Enterprise. It has 36 algorithmic qubits, 3D programmable, a gate-based model. We are working currently on the product development life cycle for the next generation system, which is called Tempo, expected for the end of the year. We're shooting at about 100 qubits for that system. There are webinars out there. I highly encourage informing yourself from these webinars. They give really good insight into the technical details of the systems. And we're switching the technology. The underlying technology will be switched from so-called ytterbium ions to barium ions. They have various advantages regarding stability, fidelity of the system, and scalability. It's really scalability, super important pillar for us, performance of the qubits, and also the engineering aspect. It's very important that machines are not just like one-offs or lab experiments. At IonQ, the emphasis is on building machines so that we can ship them to customers. I personally am based in Seattle. That's the site where we manufacture machines. We have another headquarter in Maryland. We recently shipped a machine to Quantum Basel. It's very exciting for us. It was a machine that was assembled in Seattle, then shipped overseas to Switzerland, reassembled in Basel. It's fully operational now. I want to pivot now and talk a little bit about the work with our customers and partners across many different areas. So from left to right, with Airbus, we worked on various optimization problems, bin packing problems, assignment problems. We learned a lot through that engagement around optimization, about which approaches work, but which approaches are also difficult and do not scale. They have really informed our work on optimization in particular, which I will share with you in a few minutes. AstraZeneca, we're super excited about a partnership we started. We announced it to the world last year around drug discovery and health science and life sciences. Hyundai is one of our longest-standing collaborators in the automotive space, and we work with various national labs around the globe, and we work also with a company called ANSYS in the computer-aided industry, computer-aided engineering industry. They focus on computational fluid dynamics, simulations at scale for finite elements, and many other things. And to break down in a little bit more detail what we're doing with some of those customers, with AstraZeneca, we are starting basically building a center for quantum computation at one of their R&D sites in Göteborg in Sweden. We're exploring various use cases for quantum computing directly with them. Very exciting work for us. With ANSYS, we're looking into various ways you can improve computational fluid dynamics. There are many approaches known. Some approaches are known to be very challenging, actually. For instance, HHL approaches for the experts in the audience, they do not scale very well. There are other approaches to CFD that seem to be better, so we're exploring that with them. Also, finite element solvers have a whole stack of techniques that you need to do before you even hit the GPUs to crunch the numbers. So there's a reordering step, which is a combinatorial optimization problem, which maps very nicely to the technology we're building. So that we're super excited about that partnership as well. Hyundai, as mentioned, is one of the longest-standing customer. It's always great to see a customer renew an engagement. So we're going now into the 5th year of working with Hyundai. We explored a whole smorgasbord of applications, from image detection, image classification, to material science, GANs for materials, and also battery science. So a lot of different things explored, many papers being written, a lot of IP generated through that engagement. I want to pivot now a little bit and give you an idea of the use cases where we have most confidence in. We work with a lot of customers, and there's a lot of hype, as many of you know, in the field. Many of the things that look promising at the surface actually run into certain difficulties when you try to get near-term advantage out of them. So we learned a lot through these engagements about what things might be difficult, what things work, and you will see a common theme in the examples I show you. One commonality is they're all heavily hybrid. They have a heavy classical piece to it, and they have a quantum piece. The quantum computer helps the classical workflow in a specific way to augment it. The second commonality you will see, they have a sort of decomposition flavor to it. So we're aiming at problems at scale. We're not interested in mathematical small-scale problems. We're interested in very large-scale, real-world problems. But the obvious question is, how do you break that down into the machines of sizes that we have today? So the answer is decomposition methods. You lose usually optimality when you do that, but you can oftentimes still arrive at solutions that are better than what's known classically and sometimes even surprisingly in surprising ways. So first example is optimization. Apologies for getting a little bit technical. A wise person once told me it's good to have at least one slide that's a bit more technical. It's actually the next one, not this one. But kind of the idea is to arrive at states of low energy for an optimization problem. Low energy means good, kind of gives you good quality of a solution. On the y-axis, basically, you have the approximation ratio between the ideal solution and what you found. On the x-axis is time. This is a hybrid workflow where the quantum computer is actually in the loop. Okay, so for the experts, oftentimes there's a lot of like sweeping under the rug in this field where people train an algorithm offline and then they just do inference on the quantum machine. That clearly doesn't scale. So in the data you see here, that's actually run on the device with a quantum computer in the loop, part of the training process. It solves the problem. In this case, the data is a max cut problem. It's a combinatorial optimization problem. We applied the same method to a whole range of other optimization problems. And what you can see is on the left, those very steep waterfalls, those show how fast you hit the optimum. They're kind of, after how many iterations do you start seeing the optimal solution? That doesn't mean that you get that optimal solution with 100%. The other plots show you kind of what's the percentage of, what's the chance of getting the optimal solution. And the algorithm has this beautiful property of kind of, you can show mathematically that you will get an exponential convergence to the ground state. Of course, exponential, you cannot beat the P versus NP conjecture. It's going to be exponential in the gap size of the problem. But if you have a noiseless processor, you can literally prove that this projection method boosts the ground state, as you see in the cartoon on the left side. It's based on equations of motion you can write down for the optimization problem. The method is called quantum imaginary time evolution. Very powerful. There are many other methods for optimization, including QAOA, annealing. We're interested in those as well. We're studying them. But this method seems so powerful because it has the quantum computer in the loop, and it seems to perform well in examples. So here's an example we applied it to in collaboration with a consortium called the South Carolina Quantum Association. They were interested in job scheduling problems. So you get a bunch of machines, you got a bunch of jobs, dependencies between them. So the question is, how do you map those jobs to the machines in order to minimize the make span, which is the time it takes to make a product? And that can be translated into combinatorial optimization problem, which in turn can be formulated as these type of optimizers. And as you can see, the behavior between the noiseless simulation on the left, the noisy simulation on our bespoke noisy simulators that simulate our devices, and the actual run on the device on the right, they're all very similar, indicating that the performance of these algorithms is good. So we're looking into problem encodings that are efficient, where we can scale this out to very large numbers of jobs and machines. Another example is graph partitioning. That's a problem that arises often in problems where you try to pack, say, computational loads onto multiprocessors. And here you see the typical V. The V means you start on the left with a very large problem in the upper left side. So successive decompositions, you break it down, you distill the problem into a core essence. This sub-problem we solve on the quantum machine. get a separator, so-called separator for the two graphs, and then there's a way to reconstruct it and get a separator for the original problem. This we apply to various problems. One is graph partitioning, and through work there in the high-performance simulation space, what you see here is exciting data from quantum devices, from the performance. You see the red curve is an industry tool. It's literally what people, when people use finite element simulations, it's kind of the merit factors they will experience. Okay, and you see it broken down here. It's kind of hard to read. It's a bit of an eye chart, but it goes from 10-qubit subproblem to 32. That's the largest we can do right now in our devices with this algorithm. But then on the right is also shown 10,000 and 50,000, which is the subproblem sizes used by the industry tool today. And lower is better here. It's kind of the number of non-zero elements. What's interesting is that we found solutions through this quantum sampler that already beats the industry tool at size. At 50,000 subproblem size, we arrive at solutions through this decomposition process that are better. There's very little mathematical beauty in it. It's literally an industry tool. You stick in solutions you found from a sampler, and you want to know, is it better or not? And at the end of the day, we really want to know the wall clock times of this. So this is something we're very excited about. We believe there's a lot of potential for many different industries. Yeah, and the trend goes down. The larger you can solve the subproblem with a quantum computer, there seems to be a trend that the overall solution improves. I want to pivot now and talk a little bit about quantum and AI, and then also about chemistry and materials. Those are two other areas we have a lot of conviction in. So in the AI space, I want to start with an example where it's really about feature generation. So it's about getting information from unstructured data. Think of data as given to you as a point cloud, unstructured. TDA, topological data analysis, is a method to learn structure of the data. Basically, can you understand the shape of the data in a way that's robust against rotations, noise, and so on? It's a well-established technique, not invented here by us, but it's a very promising algorithm. It's so-called the Betti number algorithm. Roughly speaking, what it does, it takes your points in a point cloud and blows little spheres around them. They will start intersecting with each other. They form a graph, right? That graph gets bigger and bigger, becomes a simplex. When you make them very large, everything is connected to everything. You get a very boring graph. So there's this behavior of increasing the sphere size that brings certain features to life, and then they die because things get too big. So that's often called a life-death chart or a bar chart. And what you can see in the lower right corner is like an application of that to MRI data. So we can see functionally very different behavior for a patient with Alzheimer's disease, a young person and an old person, but healthy person. You can see in this life-death chart that it's qualitative and quantitatively very different for the disease scenario and the healthy person. And it literally all comes from this unstructured method of trying to understand the shape of the data. Why is this interesting quantumly? Well, quantumly, you can get access to higher order, higher dimensional topological information. The typical use case that have been done classically are just one-dimensional. Those are cycles. And some papers talk about holes, two-dimensional. We can go up to dimension 7 easily with a quantum computer. It scales exponentially, though, classically in the dimension of the problem. And we applied it, for instance, also to time series data. There are multiple ways you can convert a time series into point clouds. And now you can ask yourself, is there structure in the point cloud that we can extract? We can use it, for instance, for forensic purposes to understand maybe was there an intruder in a network, looking at network traffic or things like this. Or also, can we use it for prediction of events, extreme events in market, of trends, and so on. So we did it for a basket of stocks, volatility data, and some indices. Put that together and looked at homology of up to order 4, and found that the features we could extract actually have predictive power. We looked at some correlation coefficients, compared it also with some classical, pretty simple indicators like MACD, but this is an interesting area that we're exploring currently with a few financial institutions. Finally, I want to say something about quantum and AI. There's a big hope, there's big expectations. We try to make meaningful statements about it. There are some proof points that quantum machine learning can actually beat classical machine learning. I need to give you some context. My bias is actually strongly against this because I don't understand it from my training as a computer scientist. Shor's algorithm I can understand, right? I can understand where the speed up comes from. With quantum machine learning, it's not so simple. There seems to be a consensus in the community that quantum machine learning models can have an advantage, but nobody can really put a finger down why that is. But we're pragmatists. We want to kind of just take it if there is an advantage. We want to just use it. Okay. So one theory is that just quantum decision boundaries can be higher order. You get for the same price, you get a higher order decision boundary which can fit the data better. Hence, you need less data. We see that, for instance, for quantum convolutional networks. For some use cases here, there's a sign classification problem we did with Hyundai. Indeed, it seems like there are less parameter needed. Hence, there's less training data needed to get the same performance, indicated by those stars in the upper right-hand corner. Those are the model sizes of the quantum model, around 60 parameters. The classical models need many more parameters to get to the same performance. So that's the inspiration. But this is just a small thing, right? This is just a tiny tool. We want to put that in the context of a bigger and more useful task. And that task is to take an AI model that's been trained or kind of for a specific purpose, say token prediction. Now we want to kind of give it a new capability, fine-tune it so that it can do a different thing, say sentiment analysis, intent analysis. So our current exploration in that area is to kind of strip off late layers of the existing pre-trained model and add quantum layers to it. Very exciting. We have a big campaign running right now on a leadership facility in the United States to explore this further. Come see me after the talk if you want to learn more about this. And finally, I want to say something about chemistry. So here, the big picture is there's many approaches that have been proposed for chemistry. VQE is one that's very straightforward, but it doesn't seem to scale very well to good accuracies. It has this 1 over epsilon square scaling, and you want to get epsilon accuracy. It just doesn't work in practice. On the other hand, you have the gold standard, which is quantum phase estimation, which scales as 1 over epsilon. Beautiful, but requires very deep circuits. That means you need a fault-tolerant machine. We want to get advantage much earlier. We want to get advantage now. So we developed a technique called quantum Monte Carlo. Specifically, we enhance quantum Monte Carlo samplers by auxiliary fields that we can evaluate with a quantum machine in the loop. So that's a capability that doesn't exist classically. The method is not new. Classically has been around forever. It's just been blocked classically because you cannot compute the overlap between two quantum states in an exponential size Hilbert space. Now we can, right? There's a quantum computer. We can evaluate the overlaps, and that's literally all you need to do, compute some overlaps. And so this method is, again, quantum imaginary time evolution based. I'm going to skip through this. Just want to get the plug-in. The scaling with the number of orbitals is quadratic, which is good. But in practice, even a quadratic function can be difficult on a noisy quantum system. And the post-processing is extremely heavy. It scales as a polynomial, but it's a high-degree polynomial. So we're looking into ways to accelerate that with GPUs. Here's an example why this method works well. Small system, just a hydrogen chain. But you see up top is the classical AFQMC method that doesn't have the capability to compute these inner products, whereas the quantum method actually hits the ground state energy very, very fast. And so we're working with NVIDIA and their stack and their platform to bring this workflow to life. It's a hybrid workflow. It has a classical preprocessing step. Then it has a step where you take so-called shadows. Those are like little snapshots, like tomographic snapshots. You acquire some data in a one-round process, and then you crunch the data. It's just like classical post-processing from then on. So we're getting some help from NVIDIA with that hybrid workflow and with the GPU acceleration. Looks extremely exciting. We scaled it so far to 24 qubits. There doesn't seem to be a limit other than the classical post-processing, but that's a good problem to have. We can chip away at the speed of that post-processing. I want to stop here and thank you for your attention. Glad to take questions if you have any.